Hello everyone, I am Jose and I'm going to talk to you about SoftBound, a highly compatible and complete spatial memory for C. The goal of SoftBound is to enforce spatial safety of C by means of a compile-time transformation. SoftBound records base and bound information for every pointer as disjoint metadata. This decoupling enables SoftBound to provide spatial safety without requiring changes to C source code. Unlike others, SoftBound is a software-only approach and performs metadata manipulation only when loading or storing pointer values. Also, it's important to know the difference between spatial and temporal memory safety. The first one refers to ensuring that no out-of-bounds access to memory is, whereas the later one refers to ensuring that no access is performed to memory or to an object which has already been deallocated or has not been allocated yet. In our case, SoftBound focuses on spatial memory safety. SoftBound performs a simple intraprocedural transformation that instruments its functions to propagate and check pointer metadata. More precisely, SoftBound provides two modes of checking. Full checking mode for low overhead debugging and security critical software. It provides spatial safety and, in contrast to heavyweight instrumentation used selectively during the development process, SoftBound's full checking overheads are low enough to use continuously throughout the software development process. For security critical applications, such overheads are also likely acceptable. Store-only checking mode. It is used for lower overhead protection against security vulnerabilities and the memory corruption caused by out-of-bounds writes. In this mode, SoftBound propagates all metadata, but inserts bound checks only for memory writes. SoftBound's store-only checking overhead is low enough for many benchmarks to be used in a user protection code. But how SoftBound works? As we have commented before, SoftBound is a compile-time transformation for inserting runtime bound checks to enforce spatial safety of C programs. SoftBound is highly compatible with existing C source code because its disjoint metadata representation avoids memory layout changes and allows arbitrary casts. Consequently, SoftBound associates base and bound metadata with every pointer, but records that metadata in a disjoint metadata space that is accessed via explicit table lookups. This approach is conceptually a pointer-based approach, but SoftBound's disjoint metadata provides the memory layout compatibility of object-based approaches. Now we are going to see closer how it works. For every pointer value in the program's intermediate representation, the SoftBound transformation creates a corresponding base and bound intermediate value. Whenever a pointer is used to access memory, SoftBound inserts code for checking the bounds to detect spatial memory violations. As we can see in the first image, the dereference check explicitly includes the size of the memory access to ensure that the entire access is in bounds. This dereference check is inserted for all pointer dereferences, but such a check is not required when accessing scalar local or global variables or when storing register values to or from the stack, because we assume that the C compiler generates such code correctly. In which it refers to creating pointers, we can analyze the second picture. At every malloc call, SoftBound inserts code to set the corresponding base and bound, as we can see. The base value is set to the pointer returned by malloc. The bound value is set to either the pointer plus the size of the allocation if the pointer is non-null, or to null if the pointer is null. SoftBound implements similar mechanisms for other operations, such as pointer arithmetic or structured file accesses. Pointers must also be stored to and retrieved from memory. SoftBound uses a table data structure to map an address of a pointer in memory to the metadata for that pointer. SoftBound inserts a table lookup to retrieve the base and bounds from the disjoint metadata space at every load of a pointer value. This can be observed very well in these last two lines of code. Only load and stores of pointers are instrumented. Loads and stores of non-pointer value are unaffected. Even though loads and stores of pointers are only a fraction of all memory operations, fast table lookups and updates are key to reducing overall overheads. When pointers are passed as arguments or returned from functions, their base and bound metadata must also travel with them. To address this issue, SoftBound uses procedure cloning to transform every function declaration and function call set to include additional arguments for base and bound. This can be noted in the below piece of code, where for each pointer argument, base and bound arguments are added to the end of the list of the function's arguments. Finally, we are going to talk about some experiments and results of SoftBound. Firstly, SoftBound was applied to a suite of security violations and to versions of programs with well-documented security violations. In such a case, SoftBound detects all the spatial violations and prevents all the security vulnerabilities in those tests without any false positives. Secondly, SoftBound was tested against buffer overflow attacks. It was able to detect and prevent all these attacks in both full and store-only checking mode. As to detection of spatial bugs, SoftBound with fault checking was able to detect and prevent all of the errors. SoftBound with checking only for stores was able to detect all of the store overflows, but not the load overflows. The average runtime overhead in full checking mode is 93% for the hash table implementation and 67% for the shadow space implementation. For all the benchmarks, these runtimes overheads are likely more than acceptable for debugging, internal and external testing, and for mission-critical applications. On the other hand, store-only checking benefits the hash table implementation less than the shadow space implementation, for average runtime overheads of 54% and 22%, respectively.